Dennis. Right, so Jean-Luc sends his apologies. He can't be here. He has to be at another meeting this week. So he's asked me to present this work on his behalf. I would like the 8th author or something down on that list. Before I begin, I should say that Jean-Luc packs his slides a lot fuller of information than I ever would. So I'm going to do my best to get through all of this. But Dennis, if you could wave at me when I'm going badly over time, that would be really appreciated. Okay, so I think that the main thing that I want to make clear that perhaps Jean-Luc wouldn't have done is that this exercise is an intercomparison of models. It's not a validation of models. And those of you who were watching the presentations on Monday will notice that there's some similarities also with the presentation that Peter van Bodkum gave. And indeed, these are quite related projects. And the paper that we wrote under terabytes, which was presented on Monday, uses the scenarios that we present in this paper, but the focus there is much more on the radiative transfer schemes in operational land surface models. So the focus here is actually on much more specialized radiative transfer models on the whole. Okay, so Wang designed to evaluate the accuracy and consistency of shortwave radiative transfer formulations, typically using, etc. How it's done is to set up a series of prototype land surface vegetation simulations. And the principle is that all of these models are set up to address the radiative transfer regime of vegetation under the same set of assumptions. So they all assume things like a plane parallel turbid medium approach with certain leaf angle distributions. And consequently, they should all give the same answers for some well-determined problem. We also know that we have reference models which solve that problem very, very accurately. So the approach we take in Rami 4 Pilps is to compare other models against a standard reference model. And I should add, Rami 4 Pilps. Rami is the radiation model intercomparison site. There's been a heritage of that looking at remote sensing type kind of models. And Pilps is the project for land process, project for the intercomparison of land process schemes. Okay, so this is basically as I explained before. It's a simulation experiment, so all the canopy architecture and spectral properties are known. We're not considering things like latent heat, specific heat, and so on. We're only looking in the shortwave domain. Okay, so there's no thermal or microwave components to this. And it's not using a dynamic model. It's only the radiative transfer components of the models considered here. So there's no forcing or dynamic components underlying this. So we're not testing how well the model represents growth or any of those kind of things. So we're just providing an instantaneous snapshot at some point in time where we've described everything about the vegetation exactly. And unlike other Rami papers, we're only splitting the signal into the reflected component, the absorbed component, and the transmitted component. So, two main types of experiment. The first is 1D canopies, where we're assuming a plane parallel to the medium canopy. Grasslands, which are short vegetation, covering all the flat background, and closed forest canopies, which are basically the same but tall, and we have different leaf orientation functions describing those two different scenarios. So closed forest canopy has a random leaf distribution function, and the grassland has a leaf distribution function that is we describe as being preferentially vertical. Also over a range of different leaf area indices, a range of different solar angles, and so on. Similarly, the second class of experiments was for a non-continuous canopy, which here we're representing as spheres floating above some background. But other than that, organising the experiments in a very simple way, so we've got a range of leaf area indices, a range of viewing conditions and sun angles, and a range of background optical properties. Also, Jean-Luc wanted me to pick out the fact that in these experiments, the albedo of the canopy, the directional hemispherical reflectance, was also provided with the hope that some of the modelers would be able to use that to inform models. The concept behind this was that this is something available as an operational remote sensing, but it's something that's easier than assimilating top atmosphere radiances. So those people who saw my talk on it will have heard me make these particular arguments before. It generally has less uncertainty associated with it than variables like LAI, and the retrievals of variables like LAI are typically dependent on the dimension of the inverse rhythm. So specifically what Jean-Luc's getting at here is that we expect this to be more accurately done for one-dimensional models than three-dimensional models. Much to Jean-Luc's disappointment, only one model applied the albedo simulation. And actually, if you read the paper, that's one of his colleagues. So a bunch of models contributed to this exercise. I'm not going to go through that whole list. But one model that's in common between the paper that's coming out from terabytes and this exercise is Jules. That just happened to be a model that I contributed as well. But there's quite a range of different complexity levels of models and range of the numerical routines used to solve the scattering problem. First, most important thing perhaps for from the point of view of doing climate modelling is whether or not we get the energy conservation. And for the 1D model, for the 1D scenarios, most of the models do extremely well. In fact, all of them model extremely well. This figure on the side is in percentages, so the biggest deviation is a minus 0.06. So all of the models do extremely well. Some of them do perfectly, but that's because they enforce energy closure as part of their radiative transfer scheme. And only one of them creating more energy than is incident on the scene, but it is a very small amount. The 3D scenarios, deviations are bigger, but still only in the order of kind of +2 to -4%. But interestingly, there's more creation of energy in the energy conservation in the 3 models than there is in the 1D models. So this slide shows a comparison between each of the contribute models. So we haven't introduced the reference model here yet. And essentially the way to read this is that each row and column corresponds to one model. And essentially the green colours represent good equipment, and the red colours represent bad equipment. That has been calculated across all the scenarios that will run for each model. So that's 20-something scenarios for each case. So generally the pattern you can see is that the 1D scenarios are modelled more accurately. That's more true of absorption and albedo than it is of transmission, and the accuracy decreases as we move into the 3D scenarios. So accurate decreasing counts in complexity and decreasing in the order absorption, reflectance, transmission for 1D case, but interestingly, decreasing in the order transmission, reflectance, absorption in the 3D case. And also, I mean, although obviously this could just be chance, some of the 3D models are quite close. Now, this slide's quite complex, but this is essentially the comparison against reference data, and a calculation of chi-square in the near-infrared y-axis and visible on the x-axis for each of the models. Each for the absorption, reflectance, and transmittance for 1D and 3D cases. Each colour represents a different model. Essentially, quite difficult to see boxes here, but there's a box and a 1 chi-square line for each central waveband in each of the plots. And if the chi-square for the model lies within that box, then there's no discernible difference between the candidate model and the nominally accurate reference model we're using. The range for each of these is determined by what we assume, this factor here, about the uncertainty of the candidate model. Now,
probably the best thing to do to understand that is to read the paper, it's Geology Science 2011. But essentially, if we assume that our models are very accurate, with this point here, very few of them fall into the one squared box. It's only when we start to assume some level of inaccuracy in our models, so the dark dot is 20% certainty on the candidate model, that we start to be able to say that there's no discernible reference for the normally accurate. So, that's basically repeating what I've just said. And the final observation which it makes is that it's generally better for the near-infrared case than it is the visible case for RP, with the opposite truth for absorption. So, this colour scheme then is similar to the previous comparing all of the individual models, but this is now in comparison to the reference model for each individual scenario. So we have the individual models, and these are all the 1D candidates, so joules, Yuan, up to flies down here. This is, in these rows, this is absorption, the reflectance, and the transmission. And then inside each grid, we have different background conditions vertically and different illumination conditions horizontally. And for the 1D model, generally say, the absorption and reflectance, they all compare pretty favourably with the reference model. Some disagreement in the transmission with the model by fighting joules, which only trips over where we have an extremely bright background, this is snow underlying the canopy, and with an 8-degree sun angle. But other than that, most models do pretty well. So the main discrepancy then across board is in diffuses for the 1D cases. In the 3D cases, the same is also true for some models. We have big areas where we have diffuse illumination conditions, but also generally with increased zenith angle. So as the sun becomes further away from it, and with the albedo of the background as well. And for some models, these effects can, so you get an increase in both of these, the accuracy of both of these. But in general, unsurprisingly perhaps, for the 3D models, the 3D rather, the models perform a lot worse than for the 1D system. Some models, well, in both scenarios. Right. Going beyond that, the published paper, Jean started to look at the actually plugging in some values and comparing to some published literature. I'm going to skip through this slide. This is telling us out the actual typical cases that you might see for typical rate values in each of those AR and T terms. But perhaps more interestingly, John's gone out on some published studies where he plug in values that allow him to calculate complexes, so GPP in this case. We're using a large sufficiency model, but it gives us an indication of the likely errors that you will induce by using these models in these calculations. So for funding models, for the model grassland case, there's an Alpine medley by Kallel in 2009. Where it was able to find enough information to compare their study with the reference model study for one of the Annie cases, and finds only a small deviation between the model and the study, and we can repeat that for each of the models contributing joules, and actually we find that for GPP in the one-dimensional cases, the level of disagreement when your model goes to synthesis is actually small. Doing the same thing, but for a different probability for the 3D cases, we can do the same, but we find that the deviations are much larger, and in some cases as high as 30% for some of the models. So, there are landscapes more complex and our canopies are more broken, synthesis that we predict from using in these concentration for radius transfer is going to be a lot worse than it is for closed canopies and grassland. I think it's worth pointing out that this model also simplifies a lot because it just considers a bulk A part rather than splitting it up into layers and considering effects like sun flare and so on. So that isn't taken into account in what we're presenting here. A similar procedure, this looking at rigid forcing between different scenarios. And I'll just get through this quickly. But essentially, Sean calculated different radiative forcing at Kallel. There's been a really severe, some quite large deviations for samples here. So you've got plus only 3% change in radiative forcing for one of them. So that's not, and this is snow mountain fault where we're getting some quite high deviations. So we're going to go a deviation of 100% there for radiative forcing when considering of this nature to try and produce those kind of effects. I was just highlighting the word models. Okay, so this slide takes these results a little bit beyond what's published in the paper, taking two models, so this is the JRC two-stream model, and this is the JRC two-stream inversion patch, which is essentially the first version of this model, and calculate the Rami forcings in these boxes. This, like as a summary of some results we're seeing from the ELSA, then just added on the end here the similar comparisons for these models for much more complex case stands. So the Rami 4 project, which is not confused with Rami Pills project. Okay, I almost done. Where they modelled much more accurate and realistic stands. The point which I'm making is that some of these models, even though representing canopy structures are simple, they see quite a job of getting the reflects quite well for canopy. So,